So this is going to be a video that deals with kind of introducing the idea of capacitors, how they're used in circuits. Now, this one is not going to be calculus oriented. It's going to be supplemented by another video that will be looking at how things change as a function of time using calculus on a circuit. So this will actually be in keeping with kind of the introductory ideas of what capacitors do, how they actually operate, and it will also look at basically what the endpoints are going to be, which is useful information when you're using the calculus side. It's going to correspond more to an algebra-based course, so like the old APB or the newer AP Physics 2, where they have things like capacitors in there. But it is still applicable to APC because many of the questions don't necessarily involve calculus. Let's go ahead and get started. We're going to look at basically just a simple circuit. I'm going to put a resistor in here, and I'm going to put a capacitor in here. Now, what a capacitor is, I always describe a capacitor as a bucket storing both charge and energy. More specifically, and this is going to be in contrast to another circuit component that we're going to look at called an inductor, a capacitor stores energy, oops, helps if I spell correctly, energy in an electric field. We've talked about those in class. What's going to happen is this. I'm going to give you a rough idea just so we've got a little bit of understanding. This is not necessarily the best way to think of a battery because it's not specifically real, but it's a pretty good way to draw some good conclusions. So what I want you to imagine is this. Inside a battery, we've got a whole bunch of positive charge on one end, and we've got a whole bunch of negative charge on the other. And the idea of the battery is, let's say that they can't get through, the positives can't just go over to the negatives here, so we're going to force them to go the long way through a circuit. As we start up this circuit, after I connect it, positive charges are going to leave the battery, and they're all going to be pushing through here, go through a resistor. Now, I'm showing you one charge flowing through here, but in reality, for one charge to move, all the other charges have to move. It's kind of like a musical chairs scenario. There are charges all through this. I have a positive charge that moves here because another one moved in front of it, and another one moved in front of it, and so forth and so on. So when I show one charge coming out, that's actually just a representation of all the charges taking one step to the side in a circle like this, hence why we need the circuit. But if we can imagine a positive charge coming in here and collecting on one side of the capacitor plate. Now, one of the things that usually confuses people is, well, shouldn't this cause a problem with Kirchhoff's rules? Because now I'm going to build up a positive charge over here. I won't have a current that goes through. The current coming out of the battery would not necessarily be equal to the current going into the battery. That's not the case, and I'll show you why. We have a positive charge that comes out over here, and when it gets to this side of the capacitor plate, I want you to remember that capacitors, like all other things, are actually made of positive and negative atoms. In fact, that's what I'm not drawing throughout this entire thing. All of this is made of positives and negatives, and as a positive goes here, it pushes another positive in front of it, pushes another positive in front of it, and so forth and so on. What's actually happening is the moment this charge pushes its way out here, all the charges get pushed forward, and then over here, I end up with a positive charge that comes in, and we have positive and negative, positive and negative, positive and negative, and we have a positive come in here. We have a little bit of extra positive, and what that ends up doing, stop that, is it takes, just my luck, is it takes and pushes one of the positive away over here. So as this one comes in here, another positive is pushed out over here and makes its way over to the battery. Kirchhoff's rules are actually maintained. As we build up positive charge here, for every one that starts collecting on this plate, it will actually push an equal amount of charge, one more positive, out over here to complete the circuit. So while the charge that's coming in here is not actually the charge that's leaving, that's not what's happening in real life anyway. for every positive charge that comes in here, a positive charge comes out over here, and so it has the same current through the entire circuit. So even though we are storing charge on the capacitor, which is true, we're building up positive charge here, and we're going to end up with a net negative charge on this plate because its positive charge gets pushed over here to the far end of the battery. While we are storing charge, we have just as much positive as we do negative across from each other, so whatever positive comes in over here, an equal amount goes out the other side. This is one of the things that you want to make certain that you have down. While a capacitor does collect charge and store it on here, the way it works is a positive comes in, another positive comes out over here, and the current stays the same throughout the circuit at any given point. That being said, as the capacitor starts to fill up with more and more positive charges, the battery has only so much force it can push with. It has a given potential, and that potential will be related to, in this flawed but useful analogy, how many positives it has. So if I have 4 positives here, by the time I build up a similar amount of charge, or more to the point, I should say, a similar potential difference, we're actually going to end up with an equal amount of pushing on both sides, and the current will actually grind to a stop. All the charges will stop moving. Now, we have current that will be the same throughout the circuit at any given point in time, but as time goes on, as the capacitor starts to fill up, it gets harder and harder to push charges on here. So at the very beginning, the capacitor will act like a wire. It'll have no resistance because there are no positive charges on it yet. And so the positive charges just immediately go flying through it. They're slowed down by this resistor, as we will see, but there's no net charge on our capacitor yet. And as a result, it's actually going to act like an open wire. However, as positive charges start building up, they're going to start pushing back against the stream of positive charges that are coming in, and when we get enough of them, they'll actually stop that entirely. So in short, we're going to have something that at the very beginning, T equals 0 for a discharged capacitor, there was no charge on it, our current is going to be very high. But as time goes onward, time equals, well, not equals, how about I do time greater than 0, our current begins to drop. It gets lower and lower and lower. And eventually, as the capacitor charges, as t goes to infinity, a really long time, the current will actually grind to a stop and become 0 amp. Let's see how we can actually solve some of this. Now that we've got an idea of what a capacitor does, at the beginning it doesn't really affect the circuit at all, and then as it starts to charge up, it starts slowing down current in its part of the circuit. And as I've drawn here, if its part of the circuit is the entire circuit, then it will slow down and stop the current in the entire circuit. All right, let's say that we have a resistance of, let's go with some ludicrous numbers here. Let's go 10 ohms, and let's go that this is a 3 farad capacitor. And what I'm going to do is I'm going to install, let's say, a 6-volt battery. Here's what I'm going to do. Technically, it would help if I put a switch in here. And I'm going to say at time equals 0, I close the switch. I'm also going to tell you that the capacitor starts off with no charge, so at t equals 0, Q initial, is equal to 0 coulombs. My first question is going to be this. What is the initial current coming out of the battery? Or, in this case, the initial current in the total circuit. All right. Here's where we need to introduce another equation, one that deals with capacitors. Here's the AP equation sheet, since I'm trying to get you prepared for that. Let's see. So we've got a couple different capacitor equations. One of the big ones that we're going to need for circuits, however, is, and I don't know why they have it listed this way, but it's delta V equals Q over C. The equation is delta V across the capacitor is equal to Q, the charge on the capacitor, over C. They use a capital Q or a lowercase q? They use a capital Q, but that's fine. We're talking about the charge that's on the capacitor. Well, at time equals 0, the charge on the capacitor, Q naught, is 0. So my potential difference, if my charge is 0, 0 divided by 3 farads, well, still 0. I have a potential difference at the beginning of 0. Here's where I can apply Kirchhoff's loop rule. I go across the battery, it gives me 6 volts. I lose the potential difference across the resistor. Go across the battery, go across the resistor, and go across the capacitor. I'm going to lose the potential difference across the capacitor. And at time equals 0, right when I close the switch, this all comes up to 0 by loop rule. 6 minus this minus that, 0. Now the capacitor in this case is taking energy from the circuit while it stores charge and energy. That's why I have a negative. It is taking energy and storing it in the capacitor. We can also have a discharging capacitor, one that's fully charged, that would be a positive depending on how we've set it up because it might be giving energy. Depends on the circumstance. All right, at t equals 0, however, Q equals 0, our charge on the capacitor, which means our potential difference at t equals 0 across the capacitor is 0 volts. Well, if this is 0 and my total is 6, that means my potential difference across the resistor must be equal to 6 volts, and it is also equal to the initial current times the resistance. Well, if my resistance is 10 ohms, my first question, which is the initial current, will be 6 volts divided by 10 ohms. We end up with an initial current of 0.6 amps. That's what it starts out off as. Now, if I wait a long time, it starts at 0.6 amps, but as soon as this starts filling up, it goes from 0.6, it starts decreasing down to 0.5, down to 0.4, down to 0.3. Now, we don't know how quickly it's going to be doing that, at least we don't right now, because what happens in between the very beginning and the very end is something that we'll need calculus in order to tell. I'll have a different video where we go through and we find the equations, and we're going to find that it's actually an exponential decay. We're not going to work with that here in this video. We're just going to try and find out what happens at the beginning and at the end. The other thing that I'd like to find is this. Now that we've found the initial current, it is 0.6 amp. I'd like to say as time goes to infinity, in other words, we wait a really long time and that capacitor gets fully charged. I'll point out that our final current is actually going to go to 0 amp, not coulomb, 0 amp. Why? Well, as the capacitor gets fully charged, it will actually cut off the current and eventually drag all the current to a stop. So my current in the circuit at the end, at t equals infinity, is going to be 0 amp. What I'd like to know is, what's the final charge on the capacitor? Well, once again, we turn to loop rule. Loop rule is very important when it comes to circuits. 6 volts minus delta VR minus delta VC is equal to 0. This actually stays the same at all points, except at t equals infinity, remember our current is going to be equal to 0. And since delta VR will be equal to the current going through the resistor times the resistance, at the end, this is 0, we're actually going to find that there is no potential drop across the resistor because there's no current going through it. There's no charges bringing it energy. In fact, all the potential drop will end up over the capacitor. It has stored all the energy that it can hold under these conditions. We're going to end up with 6 volts is equal to delta VC, adding that over and this being 0. And now, with the equation that we talked about before, delta VC equals Q over C, the capacitance. We know that delta VC at the end is going to be 6 volts equals Q final over our capacitance, which I said was a laughably large 3 farad. 3 farad capacitor is very large capacitor. I did this so the numbers would be a little bit nicer. But we have a 3 farad capacitor. We have 6 volts. If I want to solve for Q final, the final charge on the capacitor, it is equal to 3 farad times 6 volts. We're going to end up with 18. And this is a great time to remind you that if you put SI in, you will get SI out. We will have 18 coulomb stored on that capacitor. This is one of those things that lets you know that we're dealing with something that's laughably large. 18 coulomb is a ridiculous amount of charge to have charged on a capacitor. And when we look at this, that's how much charge is actually on one of the plates. We have 18 coulomb and negative 18 coulomb, because as we bring in charge, remember an equal amount goes over there. All right, great. So now we know, Q final. This is the charge at the end. Now, what type of other questions can I ask? There are 2 other things that I'd like to take a look at. One is, I mentioned that a capacitor stores charge and energy. So now I'd like to know how much energy is stored on the capacitor at the very end. For that, we're going to need yet another equation, but on our equation sheet, I believe it is, here it is, U sub C. The potential energy stored in a capacitor is 1/2 Q delta V, or 1/2 C delta V squared. We can do this however we'd like, but 1/2 Q delta V sounds pretty nice. So our energy on the capacitor, UC, or also in my regular notation, E final, the energy on the capacitor final, would be equal to 1/2 Q final times delta VC, technically final. If I plug in these values, I'd have 1/2. We found that it had 18 coulomb on it, and the potential difference at the end was 6 volts. So I end up with 1/2 times 18, that'd be 9. 9 times 6 is going to be, 54? 54 joules. Once again, SI in, you get SI out. A volt is a joule per coulomb. Let's try if we use the other equation. We had 1/2 C delta V squared. Okay, well that would be 1/2, our capacitance was 3 farad, times delta V, we said it was 6 volts squared. So I'm going to have 1/2 times 3 times 6 squared, that's 36, times 1/2 is going to be what? 18 times 3. Have I done this correctly? Where's my calculator? Let's see. 1/2 Q delta V, good. 1/2 C delta V squared. So let me double check this. Maybe I did something wrong. 18 times 6 times 0.5. Nope, I got that, 54. So 6 squared times 3 divided by 2. Yep, I'm just doing things wrong in my head. There. We also get 54 joules. I was going to say I was going to get a little word. All right. This is more or less how you deal with a lot of these. Capacitors, if you have them in a more complex circuit where you have another branch, they follow the exact opposite rules of a resistor. So to find the equivalent capacitance, if they are in series, you add them as 1 over the capacitances, and that would be 1 over your equivalent capacitance. Or if they are in parallel, then you would add their capacitances outright. I don't want to sink a whole lot of time into that. One thing that I would like to ask is this. What if I take this exact same circuit and I change it out? I'm going to change out the battery with a different battery. I'm going to put in a 9 volt instead. We have a 10 ohm and 3 farad capacitor. The big question is this: how much charge do we end up with on the capacitor at the end? One of the common things that people run into is when they see the capacitance, they think that the capacitance describes exactly how much charge you can actually hold. But the capacitance is actually, if you move things around, you'll end up with this. So if I have the one that I'm used to seeing is Q equals delta VC. If I move that around, I can have C equals Q divided by delta V. The capacitance, which is a set number, gives us a ratio of the amount of charge we can store divided by the potential difference. How much charge ends up on there? is a function of the potential difference. In fact, once again, in this case, I'd have 9 volts minus 0 volts as time goes to infinity. Because the current would grind to a halt, I have nothing going through the resistor, and therefore no potential drop over it, minus my delta V of the capacitor equals 0. In that case, with the new battery, delta VC at the end is 9 volts, and that would be equal to, as we talked about before, Q final, prime in this case, I could call this prime, divided by C. I would have the following. 9 volts equals Q prime final divided by 3 farad. I would end up with the new charge on it at the very end is 27 coulomb. We could go through and we could find the energy in it, but it turns out the energy stored in it has gone up as well. The capacitance does not tell you how much the thing can hold. It's not like the idea of a 1 pound bag where it holds 1 pound. We can actually put more in there if we have more pressure, is the old way of thinking of it, but more delta V, more potential, more charges here that can help push more charges onto the capacitor. So that's something to keep in mind. In real life, capacitors do actually have a final limit where they'll actually break down. They have a maximum amount that they can hold, but that's governed by things inside the capacitor, not necessarily the capacitance itself. The final thing that I'll mention, since I talked about it very briefly, if you have a circuit like this, where you have a capacitor like this, and another capacitor like this, these are in parallel. So we would have that the equivalent capacitance, let's call this C1 and this C2, capacitance 1 and capacitance 2. The equivalent capacitance is C1 plus C2 when they are in parallel. We could redraw this with the equivalent capacitance. In the way that I do in class, we would have an imaginary capacitor that would act exactly the same as these two combined, and its capacitance, CEQ, in this case, because they're parallel, would be those two added together. This is 3 farads, and this is 10 farads. This would be 13 farad. If, however, you have capacitors in series, where we could say this is C1 and this is C2, you could have C3, C4, and so forth, we would find that CEQ for series is equal to, 1 over CEQ in series is going to be equal to 1 over C1 plus 1 over C2. It uses basically the exact opposite rules of what the resistors use. If there's time at some point, I can show you where these equations come from. You can derive them with the Kirchhoff's rules and the relationships that we've been using. For resistors, you would use Ohm's law, delta V equals IR, and for the capacitors, you would use the one that we introduced earlier here, Q equals delta V times C, or some other amalgam of that. In fact, this is not how they show up on the modern AP equation sheet, but these are the ones that I'm most familiar with and use primarily in class. Here's a brief rundown of capacitors. Takeaway messages on this. Kirchhoff's rules still apply at any time t in the circuit. When you have a capacitor, or as we'll find later, an inductor, the current will actually change as a function of time. So the total current will be different for different times, but at any frozen time, t equals 3 seconds, the current here will be equal to the current here, and here, and here, and here. Kirchhoff's rules will still apply for any frozen moment in time. Big things to keep in mind. Capacitors, as they charge up, they will stop letting current go through them and grind everything to a halt. When they are discharged, when they don't have anything on them, they act exactly like a wire. They have no effective resistance. But their effective resistance goes up to infinity as they begin to charge up. Eventually, they will stop letting charges through at all. This results in things that we